Now if we could only get the Mac to work on the... Let's try this again. Here we go. Okay, everybody's going to have to come up and crowd around my screen. There we go. Don't touch it.
Yeah.
Now, I can't see that on this screen, so I'll do my best. So thank you very much for having me here. We're very excited to talk to you today. We're applying some historically generated technology from the mobile industry into augmented reality headsets and working with a number of, We're applying some historically generated technology for the mobile industry to create a 3D depth platform for augmented reality as well. Thanks for the cue, by the way. So the company, just a little bit about Pelican. We were first founded in 2009. We've been working on array depth sensor platforms since that time frame. We think we have the best array image sensor technology in the market. And I think that for the headset market, it may be one of the better technologies applied to that market. So I want to go in a little bit and talk a little bit about the evolution of our technology so that you get a sense for why we think it's good for this market. One of the first iterations of our technology was a custom 16 image sensor chip. So we had 16 image sensors on a custom 4x4 array, custom silicon, single piece of silicon, matched with a single piece of plastic to create the, with 16 lenses to create the array. Now, out of that, this was supposed, aimed for the mobile market, perhaps the hardest market to put something like this in. We were going to generate, and have generated, the RGB images for still image and video image at 30 frames per second, along with depth, all wrapped up into a standard still or video file. Now that is very computationally intensive and something that we are still reducing in order to get into the mobile devices. One of the ways that we have reduced that compute is to separate the RGB stills and video from the depth and 3D capture itself. So by doing that, we're able to create smaller arrays. We reduce our compute by more than half. So if you look at the center 2x2 array and the array on the right here, center array is a 2x2 constructed on a 14 megapixel sensor where we've separated that sensor into 4 regions, putting 4 different lenses on it, creating a 2x2 array that can scan and give you 3D depth maps and 3D point clouds. The array over here is essentially 4 720p sensors arranged around the primary camera module of the smartphone. As that camera captures RGB stills and RGB depth, we capture RGB video. We capture simultaneous depth measurements, and we marry that or co-locate that to the features in the RGB still or video. And as I said, because we started with custom and we're going to off-the-shelf parts, we've not only reduced our costs down, our compute costs down to less than half, but we've reduced our BOM costs by about 75%. Essentially what we're doing is we're taking that technology and we're applying it to custom iterations working with OEMs to create multi-baseline array depth sensors for augmented reality headsets. That gives you essentially the baseline required to get simultaneous near field depth of very high quality, far field depth of very high quality because you're using the arrays for each array for near field depth, and then the combination of the arrays as they verge together for farther field depth. And that can be aided by simple pattern light sources for flat surfaces and things like that. Now, what essentially our software in conjunction with these designs does is it takes the edge maps and the textures and creates solid objects out of them. So the pattern light simply gives us more non-visible cues to create solid objects. So that's a little bit about Pelican, but the billion-dollar question is, as Tim was talking about and several other people were talking about earlier, how do you integrate real and virtual objects in a way that augments for headsets? How do you do something as pedestrian as taking, if this is a virtual object, let's say, placing it on a table in front of you. Unless you know where that table is, there's no way to actually get it accurately in front of you in a way that will trick your mind to thinking it's there. There's no way to actually grab it and move it unless you know where your hand is in relation to the object. And as the gentlemen were speaking about occlusions earlier, there's no way to know which portion of this object should occlude my hand, should hide my hand as I look at it, and which portion of the object my hand should occlude. So depth and 3D information essentially gives us the ability to go to that next step. So this is just another version of what I was talking about. 2D images just simply lack context. You don't know how large that hand is with relation to the bottle behind it and the elements around it unless you have a high-quality, dense depth map to show you that. So, yes. And the software that we've created over time. Really, we are a technology and software company that creates arrays to the specifications of the OEMs we work with. So as we see it, 3D capture requirements for this market, near field, you got to be within 1% error. Really far field, you need to be near 1% error, but it depends on the distance you're talking about. You need to do that simultaneously, and that's a trick. In our technology versus several other types of technologies, we have a flat power band, so no matter how far out we're going to get that depth, we don't consume any more power. In a structured light or time of flight situation, the further out you go, the more you consume, because you're pulsing something out and you're getting it back. You've got to be able to work in low light situations indoors and in high illumination situations outside. And that, again, is a stumbling block for some of the technologies. Because we get our information essentially passive, we can work in both environments similarly well. You got to real-time process it and then generate the 3D scene structure. So a little bit about the competitive technologies. I don't want to go too far into this, but coded light, structured light, I don't think it really works in this iteration. Mainly because you've got an IR pattern, and if you're outside, you can't see that pattern at all. You can't recover it at all. So even if you're near a window, you're not going to be able to recover it. Plus, these things tend to be relatively thick and consume a relatively large amount of power. Time of flight is similar in some ways and different in others. If you're trying to get depth further out, you're going to consume more power. If you're trying to find something very close in, you won't consume nearly as much power. They tend to be a little bit thicker, not as thick as perhaps coded light, but still thick for going into something you're going to want to wear on your head comfortably. But why don't I wait until afterwards? Thanks. with stereo, we're actually a version of stereo. We have more than two image sensors. We believe that you need more than two image sensors, because with only two image sensors, you get very noisy depth. And with more than that, you can clean up the depth in a way that's more usable. Plus, when you're looking at stereo in this type of market, you're going to want the stereo to be at least interocular distance. So each image sensor about this far apart. And you don't then have depth until the field of view of those two cameras come together. So in front of your face, you've got no depth whatsoever. And if you move it out even further, you exacerbate that situation. The other problem with stereo is because you only have two cameras. You're talking about headsets that are going to be dropped, going to be sat on by your kids. If those cameras get out of calibration with respect to one another, the data gets corrupted, and you've got to go and have them professionally calibrated, which is kind of a non-starter for headsets. So I'll go into our solution a little bit better. It's a blow up of what I showed you earlier. Underneath that, essentially we have multiple arrays. Now, why do we have multiple arrays? Why not just one array? Because one array gives you near field depth, and two arrays used in conjunction with one another gives you further field depth. By putting cameras closer together in a single array, you get depth right near your face. So you can see your hands and what they're doing with very high accuracy. When you want to go 4 meters out, you really want to use multiple arrays so that you can interact with high precision at that distance. And again, when we're interacting at that distance, from a power perspective, our power is flat, so we're consuming no more power than we would otherwise. We can also, because we have this number of image sensor modules, we can dynamically calibrate on the fly in the field, and that is a huge deal. That means when your kid sits on your headsets and you lose calibration, you can turn them on, stick them on your face, and they will regain the calibration. And because we're a software solution, we can sit on multiple platforms. So benefits for augmented reality, better depth results indoors and outside. Low power implementation, we can recover calibration. We have no interference with multiple devices, so you can use multiple headsets in the same room without them interfering with one another. And we minimize occlusion zones by using the near field arrays and the far field arrays together. So next question from somebody in the audience is going to be, what's our depth accuracy? And this will give you a sense for our depth accuracy over distance. And that's the question. Beyond power over distance, what's the accuracy over distance? There's a number of different things that go into that when you're using a passive approach, but one of the biggest ones is how far away the baseline between the cameras, and in our case, the baseline between arrays of cameras. So we get high depth accuracy from 10 or 20 centimeters all the way to 5 to 7 meters, and then it rolls off from there. So I've got a video to kind of talk a little bit more about the importance of depth in imaging. The video features our CTO, Kartik Venkataraman, Raj Talluri, who's the SVP of Qualcomm, and Hao Li, who's an associate professor at USC.
Just turn the volume up.
Yeah. And we will see if this will work.
Ever since photography has existed, we have been capturing the world in 2D. But we see the world in 3D, and it's finally time that we begin to capture the world as we see it.
Moving forward, one of the key areas of imaging will be depth sensing. Passive sensors, such as an array of cameras, it has many advantages. The ability to not just capture a picture, but to capture the depth information of the scene.
The advantage of that is, first of all, it consumes less power, and it's sort of like the natural way of seeing things.
I think there's no question that depth is the next paradigm shift in imaging, especially in mobile imaging. If you have an array camera design, you certainly have a situation where you can make it much more manageable in size, and it'll probably fit into your pocket.
If we can make these kind of things available for consumers, then anyone at home would have the ability to actually create their own content in the way they want.
It's going to change the way people look at themselves. I mean, if you look at what is the biggest trend today in imaging, it's selfies. Now, I think that's going to be replaced by 3D selfies.
You can basically generate a three-dimensional object of yourself, right? You can basically create a 3D avatar.
And some of the applications you can think about are things like shopping. Let's say you want to shop for a couch. You look at it, you're not quite sure how it's going to fit in your house. Now, if you had a depth camera, you could take a picture of that in depth, in 3D, and then virtually figure out how it's going to fit in your living room before you even buy it.
Array cameras, of course, provide you more than just depth because you have so many different cameras. You can actually use some of the cameras to capture information that gives you better spectral resolution as opposed to just the spatial resolution which we have today.
What is the next step? What is the thing that could actually make everyone have a personalized experience and more immersive experience?
I don't think users really care whether it's an array camera or it's any other kind of camera. I think what users want is an excellent user experience. They want to be able to capture the shot they want at all times. They want good image quality in low light and in high light, and they want the convenience of being able to edit the image. Now, the beauty of array camera is that it allows the user to enjoy all of these functionalities. It sits behind the scene and provides a basic framework that enables these things to be implemented.
If we can give computers the ability to see, it's actually the next step of giving them the ability to think. And that's amazing.
So I aspire to be as cool as Hal Lee, right? I think we all should. No, right? He's impossibly young and impossibly smart. So we are in booth 109. If you want to come see a demo. Does anybody have any questions? Yes?
Should 6 cameras be all IR infrared cameras? Or
I'm sorry?
I don't see any RGB cameras. Are they all 6 or IR cameras? Or
Yeah, so they're all sensitive to visible and IR.
the RGB IR?
Yeah.
Custom. And what's the smaller baseline and the large baseline?
So the baseline between the image sensors within a particular array is about a centimeter. The baseline between the arrays is anywhere between 12 to 14 centimeters, depending on who we're working with and what the requirements are.
And the focus, because there's none of them are autofocus modules, right? They all fixed focus modules.
Yeah, so that's a. Go ahead. I'm sorry.
Yeah, just curious, how do you do that?
They're all fixed focus,
Yeah.
right? And because of that, our modules are only, first of all, they're off the shelf. Secondly, they're only 2.5 to 3 millimeters thick, which is a big deal when you're trying to integrate them into something that's going to sit on your face and weigh on your neck.
Yeah, so we take the macro and infrared photography.
Yeah,
It's doable.
yeah.
Are there any consumer devices out there that have that kind of array, yours or competitors, or how does that look like 2 years down the road?
So there aren't yet. What's happening in the devices right now is stereo for passive capture. People are finding out how kind of crappy stereo is. It's really kind of a noisy depth map, and the calibration issue is pretty severe. If you drop the phone, or if you drop the device, if you drop the headset, you essentially compromise your ability to capture the 3D information.
So what do you have in the pipeline? When can we expect a consumer device with an array? I mean, if you had one
Yeah.
of the SVPs of Qualcomm on board, then it seems like, well,
Well, from your mouth to his ears. So we're working with both mobile handset providers, and we're working with some of the AR guys. And we're looking at this point at least Q2 of 16. Okay, thank you very much.